Okay, welcome. I'm S. Masta, working as assistant professor in Annamacharya University, Rajasthan. Today we are going to discuss one topic here. The topic name is binary search tree. Okay, this is the topic from data structures and analysis of algorithms. Okay, binary search tree. What is meant by binary search tree? Okay, before going to the binary search tree, you are all thorough with, I think so, binary tree. Okay, we'll recall what's the definition of a binary. What is a binary tree? A binary tree is a tree where it contains at most two children. Okay, what here means at most two children means some people will say what is a binary tree means a binary tree is a tree which contains exactly two children. No, it is wrong. Okay, what is a binary tree means a binary tree is a tree which contains at most two children. At most two children is either it may contain zero children, or it may contain one children, or it may contain two children. Then it is called as a binary tree. Okay, what is a binary tree means? A binary tree is a tree which contains at most two children, either zero children, either one children, or either two children. Then it is called as a binary tree. Then coming to the binary search tree. Then what is called as a binary search tree? Okay, see here, we're having definition here. A tree is said to be a binary tree, or sorry, a binary search tree if every node of tree satisfies the following conditions. When a tree structure can be called as a binary search tree means it should satisfy compulsory these two conditions. What are these two conditions? Let us see the first one. The element at the root node, the element at the root node must be greater than the every element in its left subtree. The first condition. And the second condition is the element at the root node must be less than the every element in its right subtree. These are the two conditions it should satisfy when we have to confirm a tree structure is a binary search tree. Okay, here we are having a structure here. Now we will decide whether this tree structure is a binary search tree or not. If you are not thorough with these two conditions, I'll explain the same conditions in a simple manner. Okay, see, for example, we are having one tree structure is there. Okay, now observe this tree structure. I'm going to tell one more simple definition. What we can say is here also it should satisfy two conditions. That is, what I will say means all the elements in the left subtree, the elements which are in the left subtree. What are the left subtree elements? We already know that the tree properties, left subtree, right subtree. Now, what is the left subtree and right subtree elements are here? First, we will see what is the left subtree elements we are having. See, 5, 4, 6, 8, 10. All these elements are called as the left subtree elements. Okay. Now, what is the right subtree elements we are having? This 17, 19, 43, 31, 49. All these are called as right subtree elements. Now, what I will say is the same two conditions. All the elements which are at the left subtree, all the elements which are at the left subtree should be less than the root node. This is the root node. What is the root node? Here it is. 11 is the root node. Okay, what I'm saying here, all the elements in the left subtree should be less than the root node. Now compare all the elements in the left subtree with the root node. 6 less than 11, 4 less than 11, 8 less than 11, 5 less than 11, 10 less than 11. Now all the elements which are at the left subtree are less than the root node. Then take the one second. All the elements which are at the right subtree. All the elements which are at the right subtree should be greater than the root node. Should be greater than the root node. Now compare all the elements in the right subtree with this root node. 19 greater than 11, 17 greater than 11, 31 greater than 11, 43 greater than 11, 49 greater than 11. Now all the elements which are at the right subtree are greater than 11. Now we can say that this tree structure is a binary search tree. This tree structure is a binary search tree. Not only that, now compare all the left subtree elements also. All the left subtree root elements. For example, take here 4 is root element to which element? 5. Now 5 is greater than 4. Then where it is placed? If it is a greater than root element, it is as a right child. Now 6, it is the root element for 4 and 8. 4 is less than root node, then it is to the left child. If it is 8 greater than the root node, it is placed as a right child. Now 8 is root node to 10. Now compare 10 with 8. It is greater than 8, therefore it is placed as a right child. Now we can say that this structure is a binary search tree. Okay, now we'll see how to insert elements in the binary search tree, or we can say that how to construct a binary search tree by taking these elements. Here are some example elements are there. Now here it is 11, 6, 8, 19, 4, 10, 5, 17, 43, 49. All these are called as some example elements to construct a binary search tree. Now I will construct one binary search tree by taking all these elements, or I'm going to insert some elements into the binary search tree. For example, I'm taking the first element. First element I have placed as a root element. What is the root element? Here it is. 11 is the root element. Next, take the second element, 6. Now, where I have to insert this 6? According to the binary search tree rule, we have two rules or two conditions. Compare this 6 with the root node. Now 6 is less than the root node. If it is less than the root node, where we have to place? We have to place it as a left child of the root node or left side of the root node. Okay. Next, take the next element, 8. Where we have to compare this element with the root node, starting from the root node. Don't compare the element already inserted as a left child or right child. From where we have to start the comparison? We have to start the comparison from root node. Okay, now compare this 8 with this root node. Yeah, this is less than the 11. If it is less than the 11, where we have to place? We have to place as a left child. Here in the left side, already it is filled with the 6. Okay, now what I have to do? Compare this 8 with the 6. Compare this 8 with the 6. Now 6. Now 8 is greater than 6. Therefore, where we have to place? We have to place it as a right child. Therefore, I have placed it as a right child. Then take the next element, 19. Compare this 19 from where we have to compare? Root element. Don't forget that. 19. Okay, now compare 19 with 11. Greater than the root node. If it is greater than the root node, what is the rule? I have to place it as a right child. Therefore, I have placed 19 to the right of the root node 11. Next, take the next element, 4. Now compare this 4 with 11. 4 is less than 11. Where we have to place? To the left child, as a left child. Left already filled with the 6. Then compare 4 with the 6. Less than the root node. Then where we have to place? To the left side of the 6. Next, take the next element at 10. Compare 10 with 11. Okay, 10 is less than 11. Where we have to place? To the left side. Left side already filled with the 6. What I have to do? Compare this 10 with the 6. Greater than this 6. Where we have to place? A right child. In the right side already it is filled with 8. Then what we have to do? I have to compare this 10 with the 8. Then where we have to place? We have to place it as a right child. Okay. Next. 5. Compare this 5 with 11. Less than. Go to the left side. It is filled with the 6. Compare 5 with the 6. Less than. Go to the left side. Left side already it is filled with the 4. Okay. Now compare 5 with the 4. 5 is greater than 4. Then where we have to place? As a right child. Okay. Next. Take the next one. 17. Compare this 17 with 11. Okay. 17 is greater than 11. If it is greater than, we have to place it as a right child. The right side, it is already filled with 19. It is already filled with 19. Now compare this 17 with the 19. Now 17 is less than 19. Therefore, I have placed it to the left child. Then take the next element, 43. Compare 43 with 11. Greater than 11. Place it as a right child. Right side it is filled with 19. Compare 43 with 19. 43 is greater than 19. Therefore, I have placed it as a right child. Then take the next element, 49. Compare this element with 11. If it is greater than 11, where we have to place? To the right side. Already filled with the 19 and go to the right side. It is already filled with the 43. Now compare 49 with 43. Now 49 is greater than 43. Then where we have to place? We have to place it as a right side of the 43. Then 31. Compare 31 with 11. Greater than root node. Then where we have to place? To the right side. Right side already filled with the 19 and compare 31 with the 19. Greater than 19, place it right child. 43 is already filled. Compare 31 with the 43, then where we have to place as a left child. Therefore, I have placed 31 as a left child of 43. Okay. Now, this is called the insertion in binary search tree. Okay, after inserting all the elements, once compare the rules or conditions, if it is satisfied the two conditions or not. Check all the left subtree elements. 6, 4, 5, 8, 10, all are less than 11. Then check the right subtree elements. 17, 19, 43, 31, 49, all are greater than root. Therefore, we can call it as a binary search tree, or we have done insertion in the binary search tree. Okay, now we will see one simple algorithm here for binary search tree. Okay, see here. If root is equal to null, if there is no any root node, what we have to return? There is no any element, null. There is no any element. Okay, if the number, insertion number equal to roots data. If the insertion element is the first element, if it is the root data, return it as a root data. The first element as a root data. Next, if the number is less than the root data, if the number is less than the root data, that means when I compare the element with the root element, it is less than the root data. What I have to return? Return search root left. Where I have to search if it is less than the root node, where the element should be. It should be compulsory at the left side. That means left side. We already know the two conditions. Next, if number is greater than the root data, the number is greater than the root data, where I have to search. All the elements which are greater than the root data will be placed to the right side of the data, right side of the root node. That means return search in the roots right subtree or roots right side. This is a simple algorithm for binary search tree. Okay. Now we have seen the insertion. Now we will see the deletion. How to delete the elements, the binary search tree, and what happens if I delete some elements in the binary search tree. Here also we are having three cases are here. Okay, we are having three cases. First one, or we can say it we are having three situations also or three cases. First case, if I am deleting one element, if it contains zero child, that means if I am deleting one element, it does not contain any children, no problem. Simply delete that element. If you want to delete 31, just simply delete that data. For example, in the given structure, see observe here. If I'm going to delete 31 in the binary search tree, if I'm going to delete 31, no problem. There is no any child, That means there is zero child for this 31. What I can do? I can simply delete this element. No problem. There is no any problem here. Next, check the second condition. If the node contains one child, the node contains one child. For example, if you want to delete 4 in the structure, what I'm going to do? Just delete the data 4 and replace the child 5 to the left of 6. Okay, see here how I'm going to delete the element 4 here. Now, 4 element, how many elements it is having? How many childs it is having? It is having only one child. If it is having only one child, okay, if it is having only one child, what I can do? Simply delete the data. Simply delete the data. And what I have to do? Simply delete the data and place the. See, what is the second condition? Here it is. And replace the child 5 to the left of 6. What I am going to do here? Now I am going to place this 5 at this place. I am going to delete this 4. I am going to 5 and place the 5 to the left of this 6. Okay. There is also no problem. It is also very simple. Now here is one more problem here. If the structure contains two children, sorry, if the node contains two children, okay, if you want to delete 11, okay, if you want to delete 11, here we are having two situations are here. Here we are having two situations. Okay, one is the, what is that situations? One is in order predecessor and one is in order successor. One is in order predecessor and another one is in order successor. Okay, that means what is meant by in order predecessor? See here. What is meant by in order predecessor means the largest element from the left subtree of that node 11. What is that node? 11. Now, what is that root node? It is 11. Root node it is 11. That is the largest element is 10. Okay, what is the largest element from the left subtree? Observe here the structure. Now, what is the third condition means? If I want to delete 11 here, if I want to delete 11 here, how many elements are there? They are having the left elements are there and right elements also there. Now, what I can take means, if I am going to take the condition as a in order predecessor, if I am applying the in order predecessor, what I can do? I have to choose one element among these left subtree elements. I have to choose one element which is greater than the, sorry, which is the highest element, the largest element in the structure, in the left subtree. Okay, which is the largest element in the left subtree? 10. Therefore, 10 is placed at the 11 and 11 is deleted. See here, see the structure here. What happened here? I have removed 10 here and placed at the root node. And when we place at the root node, it should satisfy the again binary search tree rule. Don't forget that. Now check all the elements. 5, 4, 6, 8. Less than root node. 17, 19, 31, 43, 49. Greater than root node. No change is there. Now it is also a binary search tree. This is called as in order predecessor. One more condition is there. In order successor. What I have to do? I have to choose the smallest element from the right subtree. Okay, see in the structure, right subtree. From these right subtree, which is the smallest element? Which is the smallest element? 17 is the smallest element in this right subtree. Then what I have to do? I have to delete this 11 and I can place 17 here. See the structure here. Okay, see, I have deleted 11 and which element I have placed here? 7. After placing this structure, again check the binary search tree rule. Don't forget that. Again search the binary search tree rule. Compare these elements with root node, S less than the root node. Compare these elements with this root greater than the root node. This is called as deletion. Okay. Thank you.